the puck now. Down low for Gaudreau to Kachuk in the corner. Back to Johnny Gaudreau. Gaudreau in front. Feeds a pass to Lino. Stopped by Ottinger. Took it up high. Gaudreau scores!
In Canada, ice rinks are more than just recreational spaces. They are a cornerstone of our culture and identity. From backyard rinks to international arenas, they are where future hockey legends are born and where our nation's passion for winter sports is celebrated. They are a source of national pride, a form of cultural heritage, a symbol of our resilience, skill, and the strength of our communities. These rinks are woven into the very fabric of what it means to be Canadian. But maintaining them comes with a growing environmental cost, one that threatens the future of these very spaces. Ice rinks require a tremendous amount of energy to maintain the low temperatures for ice to freeze, typically between -8 and -4 degrees Celsius. This demand results in an average energy usage of 520 kilowatt hours per day, equivalent to the monthly energy consumption for an entire household. Spread across year-long operations in nearly 3,000 indoor rinks across Canada, this makes ice rinks the largest energy consumers in municipal areas, accounting for 40% of the corporate building emissions. Half of the energy used in these rinks goes solely to refrigeration, to keep the ice at its necessary freezing temperature. This substantial energy demand not only contributes to environmental degradation through increased carbon emissions, but also places a heavy financial burden on rink operators, making it difficult to sustain these facilities. As operational and environmental costs rise, the long-term sustainability of these rinks becomes increasingly threatened. It is crucial to find sustainable solutions that ensure that skaters all across Canada can continue to pursue the Canadian dream, a dream shared by over 800,000 registered Canadian hockey players, figure skaters, and curlers, along with thousands of more recreational skaters. To address these challenges, several solutions have been explored, though none fully meet the needs for both sustainability and performance. Synthetic ice, derived from polymers, offers a cost and energy-efficient alternative to traditional ice by eliminating the need for lower temperatures. However, these polymers compromise the skating experience, as the surface dulls blades and hinders fluid movement, making them unsuitable for high-performance activities in hockey and figure skating. Attempts at greener refrigeration methods have also faced significant challenges. Ammonia, used as an environmentally friendly refrigerant, is not only toxic and flammable, but has also been responsible for several explosions in refrigeration units, raising safety concerns. Moreover, it is costly to produce, reducing its viability as a long-term solution and highlighting the need for a tangible solution. Thus, it is crucial to develop a sustainable, long-term solution that will reduce energy consumption while preserving the skating experience.
We're RHS-Calgary, and we're addressing the energy-intensive nature of ice rinks with an innovative and sustainable solution. Our approach reimagines ice rink maintenance by enabling ice formation at higher temperatures. The core of our solution lies in the use of ice-nucleating proteins, or IMPs. These proteins naturally promote ice formation at higher temperatures compared to typical freezing processes. By applying IMPs in ice rinks, we can maintain the surface without keeping the arena at excessively low temperatures, reducing the energy required for cooling. Moreover, these proteins do not alter the structure or composition of the ice, ensuring that its quality remains intact. Our research has 3 specific objectives. First, to transform E. coli with plasmids derived from Pseudomonas syringae to produce ice-nucleating proteins. Second, to model the interactions between IMPs and water to analyze the mechanism of ice nucleation. And third, to extract the proteins and evaluate their ice nucleating capacity under different conditions to determine the optimal environment for their performance. We hope this project will encourage ice rinks to reduce their reliance on cooling systems, promoting both environmental and economic sustainability by mitigating energy costs. This approach aligns with UN Sustainability Development Goals 12, Responsible Consumption and Production, and 9, Industry, Innovation, and Infrastructure.
The aim of our wet lab team is to transform E. coli with a plasmid encoding for the formation of ice-nucleating proteins, also known as INPs. INPs are cell surface proteins that catalyze the organization of water molecules into ice. In this project, we are focusing on the INP proteins produced by Pseudomonas syringae, which have shown to be most efficient for ice nucleation. This protein consists of 2 main structures, the WO and R coils. The WO coils form the majority of the protein and feature repeating motifs, each composed of 3 amino acids that fold into a beta helical structure. These motifs contain both hydrophilic and hydrophobic groups, as represented. The hydrophilic groups, marked by blue arrows, attract water molecules, forming the active sites for ice nucleation. Meanwhile, the hydrophobic groups, shown in white, trap water between the loops of the helix structure, ensuring stability. The structure of the protein itself resembles that of ice crystals, which is key to ensuring water nucleates around the protein. The second part of the protein, the OR coils, is located in the C-terminal domain. These coils similarly contain repeating motifs but with a different amino acid sequence. R coils play a crucial role in ice nucleation and protein structure, as studies have shown that removing certain motifs reduces ice nucleation, while adding more motifs enhances it. At the end of the R coils, the C-terminus end regulates protein structure, controls activity in response to environmental change, and anchors the protein to the cell membrane. On the opposite side, the N-terminus is responsible for protein folding, tertiary structure, and facilitating ice nucleation. INPs are quite small, which limits their ability to create large ice crystals on their own. To overcome this, multiple INPs can chain together to create larger structures known as multimers to generate more ice. It has been found that larger multimers are able to form more ice. Additionally, multimers located outside the cell membrane are more resistant to pH and temperature changes. Under normal conditions, pure distilled water begins to freeze at -46 degrees Celsius without an ice nucleus. In lab-controlled settings, pure water can nucleate at -15 degrees instead. But when using the INPs from Pseudomonas syringae, ice nucleation can begin as high as -2 degrees Celsius. This indicates that these proteins have the potential to induce ice formation at higher temperatures, providing a promising solution for reducing energy demands associated with ice rink maintenance. As our project is in the proposal stage, our immediate focus will be on further research into the proteins involved in ice nucleation. Specifically, we aim to explore how INPs interact to form multimers and identify the proteins responsible for binding INPs to the cell membrane. Following this, we plan to design a plasmid containing the INZ genes from Pseudomonas syringae. We also intend to eliminate the genes that make INPs membrane-bound and instead have E. coli secreted. As the project progresses, after testing and building a prototype, we plan to incorporate further modifications, such as the addition of fluorescent proteins to increase the consumer appeal of this product.
The Dry Lab team has 2 main objectives. First, to model and simulate the interactions between INPs and water to analyze the mechanism of ice nucleation. Second, in line with Wet Lab's objectives, to test ice nucleation under variables such as temperature, concentration, and time. The first objective, to simulate ice nucleation, serves to further examine the molecular interactions within proteins, as well as revealing critical components of the nucleation process. It also enables us to predict how modifications to protein structure, such as the removal of membrane-binding parts, may improve efficiency, helping to optimize the design of such proteins. To analyze these structures, we aim to incorporate software such as GROMACS to observe protein stability and interactions under various conditions. The structure of the INP will be obtained from AlphaFold and simulated with target conditions, an ideal temperature of 0 to -2 degrees Celsius, multiple thin layers of water to replicate ice rink conditions, and gradual cooling to observe nucleation events. During the simulation, interactions between water molecules and the protein will be monitored to track changes in their structure and dynamics. To optimize the efficiency of INPs, we plan to run simulations for both the unmodified and modified versions of the protein. Through this process, we will gain valuable insights, helping us to identify and implement crucial structures that will help enhance the nucleation process. The second objective includes testing and monitoring variables such as temperature, concentration, and time during ice nucleation. A potential method for measuring the temperature at which the water has turned to ice was established by Margarina et al. In the influence of Pseudomonas syringae on water freezing and ice melting. The study utilized a solid-state thermostat with a fixed temperature, with data being recorded in real time on a computer. A similar testing procedure could be developed and refined to more accurately measure the temperature of ice nucleation with IMPs, as well as the amount of time needed. Moreover, the concentration of the IMPs is also significant in determining the most optimal conditions for ice nucleation in the application of a rink. Current research has demonstrated optimal cellular concentrations for IMP-producing bacterium, with further research and experimentation needed to determine the ideal protein concentration.
In order to achieve sustainability goals, our Human Practices team has established several outreach goals to better understand the community's awareness of energy usage and its environmental consequences. Firstly, we aim to find metrics that determine public knowledge on this issue, particularly for those who use and maintain these spaces. This will be accomplished through surveys designed to assess the general awareness of energy consumption and their contribution to municipal energy usage. Additionally, we plan to engage with stakeholders and ice rink regulators to gain insight into the challenges they face in maintaining these rinks, and how refrigeration-related issues affect their operations. Looking forward, we also intend to develop educational workshops to raise awareness about the environmental impact of ice rinks and empower users to take action, not only for the environment, but also for the national traditions tied to these spaces. By addressing the overbearing energy cost associated with refrigeration, we aim to ensure that the connection between Canadians and their skating traditions continue to thrive, whilst advancing environmental considerations through new technology.
Ice skating is a tradition that has endured for decades, providing Canadians with a sense of pride, joy, and connection to our culture. Without it, we risk losing a vital link to our national identity, one that defines us as a country. Now, more than ever, it is crucial that we take action to ensure the sustainability of these beloved spaces, using innovation and community outreach to preserve this cherished sport for future generations.